clarity when they talk to people like what? My cause is to engage in the financial sector with AI technology to develop financial skills. Okay. AI. That's Alright. See, so yeah, people who actually like get time like students, it's like keep playing with the ball to them.
Okay, we stopped off at page 38. We saw how we can graph the different types of cardioids. If I just have a coefficient with the sine or cosine, it'll just be a circle. But if I'm adding a constant to that term, then it's going to be kind of circle shape, but there's definitely something that's going on the other side, either something that resembles like a sharp turn, like a heart-shaped graph, or a loop, or something where the graph is it's moving in, but not quite all the way in. So this is dimpled Lima-san. But we know that these are going to be the types of shapes we expect when we add a constant to a sine or cosine. Next up are graphs where we have these petals. It's going to kind of looks like these flower petal graphs. So we'll look at how to recognize and what those how those graphs may look. So this is page 38, example 4. I just want to show you just some properties about this as we go as we identify some order pairs. So let me identify some properties at this stage here. So again, this is page 38. So now we still have sine and cosine involved, but there's definitely something different about these angles here. It's not just cosine of theta, it's cosine of 3 theta. We have a coefficient inside the angle there. So the coefficient in front is still representing kind of like your diameter, but we're going to call this the petal length. So the length of the petal of each of these petals is going to be 3 units. And that 3 theta is indicating to us how many number of petals. So if it's an odd number, which this one is, then it's going to indicate the number of petals. If it's an even number, then there's going to be a little difference going on. But here, if it's an odd number, then indicates the number of petals. So we're expecting 3 petals, each petal with a length of 3, and our graph is going to end up being symmetrical about the x-axis. All your cosine graphs will be symmetrical about the x-axis. So let's start off here. We'll start at 0. All right, so if I plug 0 in for theta, cosine of 0 is 1. 1 times 3 is 3. So at the polar 0 here, at this polar x-axis, we know we're going to start off at 3. I'm going to pick convenient values here. Let's say I chose pi over 6. If I chose pi over 6, what's 3 times pi over 6? Pi over 2. Okay. And cosine of pi over 2 is 0. So I'm going to hit a polar 0 here. So the graph at pi over 6 is going to come in at an angle here. It's going to come in at an angle towards the polar 0. Next up, let me choose pi over 3. Pi over 3 in for theta, which is pi. Cosine of pi is -1. -1 times 3 is -3. So now at this pi over 3 line, we want to go in the third quadrant. So we want to go away from the first quadrant and walk opposite. So 1, 2, 3. Next up, let's choose pi over 2. Pi over 2 in for theta. That's cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. 0 times 3 is 0. So we have a second polar 0. This is going to come in at pi over 2. And it's going to... So notice that it doesn't do one petal at a time. It kind of jumps around. And in this case, it starts half of the first petal and then fulfills the second petal before it continues on. Okay, keep going. Next up, I'll choose 2 pi over 3. So 3 times 2 pi over 3 is just 2 pi. Cosine of 2 pi is 1. 1 times 3 is 3. So that means at this angle, at 2 pi over 3, we need it to go all the way over to this 3 here. So the graph is going to do this. Let me choose 5 pi over 6. 3 times 5 pi over 6 is going to be 5 pi over 2, which is 2.5 pi, which is going to be 0, right? Cosine of any variation of pi over 2 or 3 pi over 2 is going to be 0. So we have another polar 0, and it's now going to come in at this angle here. And then finally, at pi, cosine of 3 pi is -1. -1 times 3 is -3. So then at pi, we want to walk away from pi and into this side. So it's going to end up being over here like this. So it's going to fill out that last petal. Again, we don't have to worry about having to sketch all these graphs, but I think it's important, just to kind of know how these graphs are formed, just to be more familiar with them. Without looking at the graph, what would you expect here? This would have how many petals? 5. Each petal with a length of 2. This is what the graph looks like. This one, sine of 7 theta, 7 petals, each with a length of 4. And then all the odd numbered degree or theta values will all complete their cycle from 0 to pi. So if it's 3 pi, 3 theta, 5 theta, 7 theta, they're going to complete all their full cycle in that interval from 0 to pi. Yeah, they're always going to be symmetrical. In this case, looks like the odd petals are going to be not only symmetrical about the x, but also about the y. It's going to be symmetrical in both directions. Okay, let's go to page 39. There's something a little different about if I have even theta values, like 2 theta or 4 theta or 6 theta. But first, the coefficient is still going to do the same thing. It's still going to tell us the petal length. So if n is even, which is the coefficient in front of theta, then we're going to have 2n petals. So if this is 2 theta, we're going to have 4 petals. If this is 4 theta, we're going to have 8 petals. If it's 6 theta, we're going to have 12 petals. Okay, so I want to show you why it's doubling the number of petals here. Sorry, R theta R. Let's start at 0. So if I plug 0, cosine of 0 is 1. 1 times 3 is 3. Okay. Let me choose pi over 4. 2 pi over 4 is pi over 2. Cosine pi over 2 is 0. So we have a polar 0 here. So pi over 4, I'm just going to just estimate where that is. So I want to come in at this angle here. Next up, pi over 2 gives me -3. So pi over 2 is here, but I got to go into the negative y-axis. Pi over 2, yeah, and then pi is at 3. I plug pi in. 2 pi is 1. 1 times 3 is 3. Oh, sorry, I skipped over 3 pi over 4. 3 pi over 4 is going to be 0. And then pi is going to be at 3. Now, if you look, normally from the previous problems, when we got to pi, we were back to where we started, right? When we got to pi, we were back to, 0, 3 is same thing as pi -3. But here, the issue is that when there's an even number of petals, when you reach pi, it's going to end up in a different location than where you started. So it's going to have to go through another cycle before it can complete all these petals. So that's why it's going to end up with 4 petals, because it's not ending in the same spot as it was as the previous one. So because it didn't end up in the same spot, it's going to continue on the process, and it's going to create more petals than the previous. So then next up, we do 5 pi over 4, which will give us 0. 3 pi over 2 will give us -3. The graph is doing. So that's the first stage. And then the second stage is going to go through another pi units before it can. So it's not going to arrive at the starting location until we get all the way to 2 pi. And because it's taking twice as long through the cycle, it's creating double the number of petals. So that's just the intro that I wanted to start you off with, that we're comfortable with how graphs are formed from polar graphs. It's really going to come in. It's going to be really important when we talk about polar area, and we have to, just kind of know how the graph is moving. But This next part is defining and differentiating polar forms. So finding derivatives is going to feel like what we did with parametric. A lot of it's going to feel familiar. It's just with polar area it's just that students tend to have a bit more, just students just need more time to let that those types of problems sink in. Okay, let's go to page 40. Okay, so a lot of this we've kind of gone over yesterday already, but just for review, XY is for rectangular coordinate system, R theta is for polar coordinate system. R is a directed distance from the origin to a point. Theta is a directed angle. In polar form, there are multiple ways to identify the same point. We talked about that yesterday. We can either walk towards or away from our quadrants by indicating a positive or negative radius. We talked about how we get from polar to rectangular. We can go through sine and cosine. We get from rectangular to polar, we'll use tangent and Pythagorean theorem. So number one, we're going to look to convert from these equations from polar to rectangular form. That means we want x's and y's instead of r and theta. So we're just looking for ways to make substitutions. Now, r cosine of theta, if you look at that, r cosine of theta matches nicely with the formula for, we can make a nice substitution there. So r cosine theta equals -4. The same thing as x equals -4. So this equation, doesn't matter which form, is going to end up looking like a vertical line. Obviously, it's a little bit, in this case, a little bit easier to look at it from a rectangular perspective than a polar perspective. Next up, 4r cosine theta equals r squared. I want to find a replacement for r cosine theta. I don't want to find a replacement for r squared. The goal is to, piece by piece, get all of these portions to show me x and y. What can I replace r cosine theta with? X. Like, what can I replace r squared with? And if I play with this equation a bit, we can turn it into something that feels more familiar. So the idea is that, what if I can complete the square here? 4 divided by 2 is 8. Sorry, 4 by 2 is 2. 2 squared is 4. So if you recognize this, this is basically the form of a circle, right? This is a standard equation for a circle. My radius is at 2, 0. My center is at 2, 0. And then my radius is at 2. My radius is 2. Number 3, 4 over 2 cosine theta minus sine theta. Not as easy maybe to interpret what this is going on, but what if we just cross multiply it here? We can get something to maybe show up. If I distribute that r through, and now we see some substitutions show up for us, right? R cosine theta gets replaced with what? X. And then r sine theta is y. So that feels a lot more familiar. We know that if we rearrange this just end up giving us an equation of a line, right? So a slope in polar form. So a curve in polar form is given by r equals f of theta. Think of your r as your it's like your y value. So f of theta is kind of like your y value. Then in rectangular coordinates, then the rectangular coordinates are given by x equals what was r cosine theta. We can represent as f of theta cosine theta just to get everything in terms of one variable. Then therefore the derivative of something that is in basically we're basically getting it into like parametric form here. So if I want to find dy dx in terms of theta, it's just y prime over x prime. But both y and x have a multiplication of two different things here. So if I want to find y prime over x prime, I got to go through a product rule here. F prime g plus fg prime, and then f prime g plus fg prime. But the minus is showing up because the cosine's derivative is negative sign, that's why. But essentially, we're just doing product rule for both of these. All right, page 41. So 41, page 41, number 4. The following is an example of a common problem found on the AP exam. What is the slope of the line tangent to the polar curve r equals 1 plus 2 sine theta at theta equals 0? So we basically have to get it into polar form or represent our basically our vertical and our horizontal components. Okay, I'll move it. So we know that dy over dx is basically dy over d theta over dx over d theta, similar to how we do with parametric. So we have to basically find the derivative of y, find the derivative of x, plug in 0 for each of them, and ultimately this is going to result in something that will be equivalent to slope that we're looking for. But let's build them one piece at a time. We know that y is r sine of theta, and we know x is r cosine of theta. Now we want to get r in terms of theta so that we can just do everything in terms of one variable. So therefore, y is equal to 1 plus 2 sine theta, then x is 1 plus 2 sine theta, cosine theta. Let me zoom in a bit. Okay, are we okay so far? We're building our y and x in terms of theta. So now we're going to find the derivative of y going through product rule. Plug 0 in, and that will represent y prime of 0. We'll go through, we'll find the derivative using product rule to get to x prime, then plug 0 in for theta, and that'll be x prime is 0. And then the resulting number will give us slope. Everybody good with that? Okay, so let's go through those steps. Sorry. So I have my y prime and my x prime going through product rule. And now to find y prime is 0, I'm just going to replace all the thetas with 0 and see what number I get out of that. Anything, well, sine of 0 is 0, so that's going to wipe out this. Cosine of 0 is 1. 2 sine of 0 is 0. 1 plus 0 is 1. 1 times 1 is 1. So I should get 1 in the numerator here in my denominator. Cosine of 0 is 1. 1 times 2 is 2. Anything times sine 0 is going to be 0 because sine 0 is 0. So that's going to wipe this whole thing out. I'm just left with 1/2. So therefore, my dy dx is just simply 1/2. So similar with parametric, it's just that with polar, that's r sine theta and x being r cosine theta. To get them into the same variables there, we're going to have to go through a product rule. So that's just the only thing there. Next up, number 5. Find the values of theta where the graph has horizontal and vertical tangent lines. Now, you can kind of tell where these tangent lines are, right? We can expect a tangent line here. You can expect a tangent line here. You can expect a tangent line there. So here we have horizontal tangents. And then we're going to be asking, where do we see vertical tangents? And we're going to make the go through our calculus to find where at what theta values are these vertical tangents occurring. Now we know what slope is, right? Slope is dy over dx is y prime over x prime. Whatever causes my y prime to be 0 is going to be where my horizontal tangents will occur, right? Whenever my numerator is 0, that's slope 0, and that's what I see, right? So anytime my y prime is equal to 0, if I'm looking for horizontal tangents. Therefore, my x prime is going to give me information about my vertical tangents. Okay, I'll start with horizontal first. Let me first build up my y equation before I can find y prime. My r is 1 minus sine theta. We'll go through a product rule. Then we'll set the derivative equal to 0 and look for theta. And those theta values will tell us where the graph is going to be experiencing a slope 0. Product rule. If I set cosine of theta equal to 0, I'll get theta is equal to pi over 2 and 3 pi over 2. If I set 1 minus 2 sine theta equal to 0, I'll get 1 equals 2 sine theta equals 1/2. And where is sine equal to 1/2? First and second quadrant, right, in that pi over 6 family. So we have 4 potential locations where we have a horizontal tangent. Oh, and one more thing is, if we see duplicate locations between vertical and horizontal results, we're going to take them out. So if there is a duplicate, then it's neither a horizontal or vertical tangent. So it needs to kind of stand on its own in order. So if we see anything duplicated between vertical and horizontal critical points, we're going to take them out. They're not going to be part of our solution. So it's not hard, right? It's just kind of tedious. So let's start. Let's do the vertical portion. So x equals r cosine theta. Replace the r with 1 minus sine theta. And then you're going to go through your derivative using product rule. Set that equal to 0. Find your critical points, and those will be candidates for vertical tangents. I'm just going to arbitrarily get one of the trig to get in terms of the other so that I can just have easier time factoring if I can just get it down to one trig function. So I'm going to replace cosine squared with 1 minus sine squared. We know sine squared plus cosine squared equals 1, right? we can factor that. So where sine equal to -1/2 is going to be in that pi/6 family, but in the third and fourth quadrants. Where sine equal to 1, sine equal to 1 at pi/2. But if you look, pi/2 is duplicating in the horizontal and vertical, so this has to be taken out. So then our vertical tangents is going to be at 7 pi/6 and 11 pi/6. But then our horizontal tangents will be at pi/6, 5 pi/6, and pi/6, 5 pi/6, and 3 pi/2. Okay, I'll split this section's homework up into 2 days. So today, if you can just focus on, let me adjust the homework here. So just do page 41 to 42. And then tomorrow we'll do 43, 44. But tomorrow, I do want to start getting into polar area. All right, go get your phones.
No, I'm the A.
Like I already picked 0. I turned it in and
It's like there's a. Yeah, so your article in that, maybe.